Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, we'll start a new session called Constraint Satisfaction Problems. So far, we talked about search problems. Constraint Satisfaction Problems, or CSP in short, are a different types of search problem than the type of the problems that we saw already. So what we had so far in search in general, up to this point in the course, we had some assumptions about the wallet where we have only a single agent. We didn't talk about situations where we have multiple agents. We have deterministic actions. We have very specific set of actions. They are known to us in advance. They are finite. So we know what are the possible actions at every state. Fully observed state, we know everything about the state, and discrete state space, where the states are discrete. So generally we have in this case, we have two types of problems. The first one is called planning problems, and this is the type of the problems that we saw before in the course. In planning problems, we try to find the path to the solution, to the goal, which is considered the solution. Okay, so the path to the goal is the most important thing in planning problems, and the path, of course, will be a sequence of actions going from that state to another, taking one action at a time. And of course, as we saw before, paths are not equal in terms of cost. So we were always trying to find an optimal solution or least cost solution. Okay, and heuristics, of course, were available to us in at least the greedy and the A-star algorithms, where we have some knowledge about the domain of the problem. So that's planning problems. Another type of problems called identification problems, where we have variables and we want to assign values to these variables. So in this type of problems, the goal itself is important, but not the path, because the paths actually are all of the same cost or length, because the path will be to assign one value to every variable. So all paths are of the same depth or length. So that's why we don't care about the actual the steps, but we care about the assignment of the variables. Okay. So or in other words, we care about the goal itself, not how we reach the goal. CSP problems, or constraint satisfaction problems, are a special case of identification problems. So let's now talk about constraint satisfaction problems, or CSPs. In standard search problem, we have the state can be anything, can be an arbitrary data structure, and the goal test can be any function over the states, and the successful function also can be anything. So that's the general standard search problem. But in CSP, it's much more specific than that. It's a special subset of search problems where we have the states to be defined as variables, okay, as a set of variables. So we have here a set of variables, xi. Each variable can take a value from a domain D. Okay, so the domain sometimes depends on the variable. Domains might be different for different variables, and the domain, of course, determine what are the allowed values for every variable. Generally, it is different for every variable. In some problems, all the variables have the same domain. And here, the goal test is a set of constraints that we want to satisfy, a set of conditions that will tell us what are the allowed or possible or legal values for the variables. Okay, that's what we mean by CSP, or constraint satisfaction problems. We have variables, we need to assign values to these variables, of course one value for every variable, so that we satisfy all the conditions or all the constraints that we have in the problem. So the goal test is whether we satisfied all the conditions or all the constraints or not. If one constraint only is not satisfied, then we didn't reach the goal. Then the goal test will fail. And because this is a very specific type of search problems, this will allow us to get algorithms that are more powerful than the standard search algorithms that we saw previously in the course. So let's talk about examples of CSP problems. The first classical example is called map coloring. In map coloring, we have a map of a country or a continent or whatever, and we want to color every state in the map in a color where two neighboring states will have different colors. So we cannot have the same color of two neighboring states. So for example, Western Australia should not have the same color as Northern Territory because they have a common boundary here. They are neighbors. Okay, South Australia and Victoria also, they cannot have the same color, and so on. So these are the conditions that we have in the problem. So what are the variables here? One formulation is to have a variable for every state. So the states here will be the variables because we want to assign a color or a value to every state or a variable. Okay, so the variables here can be the states, W, A, N, T, Q, and so on. Now the values come from the domain, and the domain here will be the same for every variable, which are the three colors that we have in this problem: red, green, and blue. As I said earlier, the domain might be different for every variable, but in this problem, it is the same. Okay, so we define the variables, we define the domains for the variables. Now what is remaining is the constraints. So the constraints here, as we said, adjacent regions must have different colors. Now we can define the constraints in two ways. One, we call it implicit, where we define the relations between the variables. So for example, we can say WA is not equal to NT. So the value of WA in terms of a color should not be equal to or cannot be equal to the value of NT. That's an implicit constraint. Now we can write the constraints in an explicit way where we specify the possible values. So for example, we can say that the pair WA and NT can take any of the values here. Can be red and green, which means that WA will be red and NT will be green. It can be red and blue, WA red, NT blue, and so on. So we list all possible values that this pair can take. When we do something like that, we call these constraints explicit because it will give us explicitly the values of the possible values of the variables. So we are specifying the constraints in terms of giving the valid values. So these are two different ways of expressing the constraints. Now the solutions will be assignments that satisfy all the constraints. So for example, in this example, I can say I will assign red to WA, green to NT, red to Q, and so on. And that's actually what we have here on the slide. If we have these assignments, you will see that none of the constraints is unsatisfied, is violated. So all constraints are satisfied, which means that this is a solution to the problem. Okay? Questions? Abdurrahman? Yes. It depends on the problem, Abdurrahman. So here, the variables in any CSP should be the thing that will be assigned a value. So here, what are we targeting? We want to map every state, right? So a natural choice here is to make the variables to be the states, and the values will be the colors. But generally, it depends on the problem. You will see we have two, I think, or three more problems. You will see that sometimes we have different choices. We can make different decisions about the variables. But eventually, the variables will be the thing that you want to assign values to. Okay, you're welcome. Any other questions? Saad? Yes, because the path. Yes, because the path of the goal is the assignment, and eventually any solution will have one assignment for every variable. Okay. All. Yes, all the variables, exactly. All the variables are assigned anyway. Yes, so that's why all the solution will have the same length or depth. Okay. Yes, Abdurrahman. Okay, that's a frequently asked question. Yes, I recorded locally, Abdurrahman. So you don't see it recorded from Collaborate, but I recorded locally. So don't worry. Okay, no problem. Okay, here's another example. I hope that will be more clear and make the concept of CSP more clear. This example or this problem is called n queens problem. We have a kind of chessboard that is square, n by n, n rows by n columns. And on that chessboard, we want to put n queens so that the queens don't attack each other. You know that a queen in chess can attack horizontally, vertically, or diagonally. Okay? So if we have n queens to put on the board so that they don't attack each other, this is what we see in the slide here is a solution, is to put one queen here, another here, another here, another here. So if you look at these 4 queens, you will find that they cannot attack any other. Okay, any pair of them don't attack each other. Okay, of course it might be easy for small boards, but if n increases, then it will be much harder. So that's a problem. We have conditions, right, which is we want to avoid attacks between the queens. So let's see how we can formulate it as a CSP. In formulating a problem as CSP, we have to define 3 things. We have to define the variables, we have to define the domains, which is defining the values that are that the variables can possibly take, and the constraints. Okay, so these 3 things have to be determined. So one formulation is to say that the variables will be the positions on the board. So every position in the board will be a variable. In this case, we will have n square variables, and in that case, the values will be either 0 or 1 for every variable, which indicates whether we have a queen on that position or not. Okay, so this is now the variables. That's one formulation. We'll see another in the next slide, but one formulation is to have a variable for every position in the board. Now, what are the constraints? We can express the constraints explicitly like that. So this constraint says that for all I, j, and k, xij and xik takes one of these values. Now, if you look at this, xij and xik, those are the positions at the same row. So here we are saying that the positions at the queens at the same row, or the values at the same row, should not have 2 queens, because we cannot have 2 queens at the same row. So you will see, we will not see here 1 and 1. You can see 0, 0, which means no queens at all in these 2 positions. 0, 1, which means 1, 0 here and 1 here, and 1, 0, which means 1 here and 0 here, but not 1, 1. So that's a constraint for rows. Similarly, we can have a constraint for columns, and constraints for the diagonals. Okay, so these are all constraints that have to be satisfied. Okay, so that's of course explicit constraints, because we are saying what are the possible values for these for pairs or more of these variables. Now, if we keep the constraints like that, then a solution to this problem can be don't put any queen on the board, because 0, 0 will satisfy zeros everywhere will satisfy all of these conditions. None of the queens will attack each other because there are actually no queens on the board. But of course, this is not sufficient constraints, so we have to add a constraint that says we have to have n queens. So we added this constraint to indicate that we will have to have n queens here. Okay, so the summation of the values of all the positions will be n, which means that we will have to have n and exactly n queens on the board. So that's one formulation. Okay, that's one formulation. A second formulation is a bit easier. Okay, and we'll see why it is easier. We know in advance that we cannot put, for example, two queens on the same row, right? So we can say that a variable is where in every row the queen will be. So there will be a variable for every row. And the value of that variable will be which column the queen will be, because we know that there will be one queen only in every row. So the question is, and it has to be in every row, right? Because we have n rows and n queens. No two queens can be in the same row, so there will be one and only one queen in every row. So the question will be where exactly in that row the queen will be. So we will have now qk as a variable. Now k goes from 1 to n. Now the number of variables is just n. Remember in the first formulation we had n square variables. Here we have just n variables, and each variable here can take the value from 1 to n. N is the number of n queens and also indicate the dimensions of the board. Now the constraints implicitly we can say none of qi and qj threaten each other. That's an implicit constraint, and we can of course we can write a programming function to do that, or we can explicitly list all the possible values for the pairs of the constraints. So we can say q1 and q2 can take 1, 3, 1, 4, and so on. Okay, 1, 3 here means that I can put a queen in the first column of the first row, so queen here, and 3 means there will be a queen here. It cannot be a queen here, right? So 1, 2 is invalid, 1, 1 is invalid, 1, 3 is valid, 1, 4 is valid, and so on. So we have to list all the possible values for every pair of rows here. Okay, just to have the explicit constraints. But implicit constraints are much compact, much easier. We can just say qi and qj will not threaten each other, and depend on coding this condition just to make sure that it is satisfied. Okay, questions? Ghanem? What do you mean by the queens themselves? You mean where will they will be? Now I have to choose the variable so that eventually I will have a solution to the problem. Okay, so if I choose the variables this way, so eventually when I say q1 is 1, q2 is 3, q3 will be 2, for example, so I can check if this is a solution or not. It gives me a possible solution to the problem that I can check if that's actually a solution or not. Okay, and in that case I can, in the previous case also I can, but this case is easier because we have less number of variables. And we have some of the constraints implicitly in the definition of the variables, because we know, for example, that no two queens can be on the same row, so we have and every row has one queen, so we will just need to know where exactly in that row the queen will be. Okay, Abdurrahman. Two questions, Abdurrahman. You asked so many questions today. طيب, okay, sure. Yeah, non-threatening means they will not attack each other based on the rules that we know. That's why it's called implicit. It's not very well described. It's not very specifically described. It's just implicit by knowing what we mean by non-threatening. Okay. Sure. Yes. Okay. The easiest one is the first and second one, and if you understand these two, you will understand these two. So for this one, you'll see that xij, you'll see that the constraint is over ij and k, and xij and xik. So I here is the same I here, which means that they are on the same row because the position is known by row and column. Okay, so having the same value here, so that means that if we have the same row, let's say that I is 0. Okay, now j and k can be will be the columns. Yes. Okay, so if you put any two columns for the same row, we should not have two queens on the same row, right? Because if that's the case, they will attack each other. That's why the possible values will be 0, 0, 0, 1, 1, 0. But you don't see a 1, 1 here because that's violation of the constraint. And the same for the others. Okay? Okay. Ghanem again. Ghanem, do you have a question? Yes. Exactly. Exactly. Yes. Yes, exactly. No, n is the size of the board, right? N times n by is the column in each row. So for example, if Q1 is 2, that means that I will put the queen at the second column of the first row. Because I want to determine where exactly in that row the queen will be. So it can be in the first column, in the second column, in the third column, in the nth column. Okay? That's why the domain. Exactly. Yes. Okay. Yeah, it was just binary, yes. Because we had the variables everywhere. No, it's not the number of queens, it's the column number. Okay, you're welcome. Okay, Hamza, did you have a question? Hamza Saleh or Salah? Okay. مش مشكلة ولا you got the answer? Okay, good. Okay, now let's talk about, okay, no problem. Let's talk about how to start to think about solving CSPs. So we'll talk about the concept called constraint graph. So what is a constraint graph? Let's first define what we mean by binary CSP. In binary CSP, each constraint relates at most two variables. So for map coloring, you saw that the constraint, every two states have to have different colors, right? So the condition here of the constraint relates two variables only. If we have a problem where all the constraints relate two variables at most, then this is called binary CSP. Okay? Notice that the constraint might relate one variable only. And for example, if I told you that, okay, with map coloring, I want to map NT, Northern Territory, with blue. Okay, that's a condition on one variable. That's okay if I have the constraints up to two variables, relate up to two variables, then this is called binary CSP. Now, for binary CSP, we have what we call binary constraint graph. So we have a graph where the nodes are the variables and the edges are the constraints. For example, like this. So this is exactly the map coloring problem, where every node here is a variable, and the edges are constraints between the variables. So there is a constraint between NT and WA, there is a constraint between NT and SA, there is a constraint between Q and SA, and so on. And if and of course for T, for Tasmania, we don't have any constraint, by the way, because it's far from the other states, so there's no conditions. So we don't have any edges coming to or from that variable. And all the constraints here relate maximum to two variables, and this is why we call it binary constraint graph. But generally, the graph, by the way, can have constraint. The graph can have constraints that relate more than two variables, as we will see inshallah in the next example. But at that point, this is a binary constraint graph because the constraints relate at most two variables. The main concept here is that we put the nodes to be the variables and the edges to be the constraints. Now, this by itself doesn't tell us everything about the problem, because we have to know what exactly each constraint means. Okay, so we should have with every constraint the meaning of it. So, for example, in the map coloring problem, that means that the values of these two variables should not be equal. Maybe in other problem that might be less than or equal to, or something else. Okay, so it depends on the problem. But eventually, generally, in the graph there will be an edge that represents a constraint. With the constraint, there must be some information about the meaning of that constraint. Now, why is that a problem? First, why is that important, the constraint graph? First, this is a way of formulating the problem, is for visualizing the problem. Second, we will see inshallah later in the next lecture probably, or the lecture after, how the graph can be used actually, or the structure of the graph can be used to solve the problem. For example, Tasmania here has no edges to the other states or the other variables. That means that it is completely separate from the other part of the problem, which means that we can solve it completely separately. Okay, so that's just an example of something that the graph structure can tell us about the CSP. Questions? Hamza? No, the bipartite graph is a very special case where we have two sets of nodes. Here we don't have this. It's just that the edges relate to variables with each other. As we will see inshallah very soon now in the next slide, that the constraints can relate more than two variables generally. Okay, now let's move to the next example. Let me okay, now in this example, this problem is a really nice and funny problem, where we want to write the arithmetic operations with letters, but still every letter should have a value. So for example, I want to write something like 2 plus 2, and I get 4, where every letter here has a value that is valid mathematically. Okay, so I want to assign a value to O, and a value to W, and a value to T, so that when I write 2, but now as in letters, but it will be interpreted as a number, plus 2, I will get 4, where also the values of 4, when I assign value to every letter here, it will be actually the correct answer to this operation. Okay, so the variables here are, or should be, the letters. So I should have a value for O, a value of for W. Of course, the value here is digit, so I have to assign a digit to every letter here, to O, to W, to T, to F, to U, to R. And not only that, because you know in mathematics, when we add two numbers, we might have a carry here, right? So O plus O is not equal to R only, it will be equal to R plus 10 times the carry. So we will assume that there is a carry here called x1, there is a carry here called x2, and there is a carry here called x3 out of these operations. So the variables here will be F, T, U, W, R, O plus the 3 carries, x1, x2, x3. Okay, and for that simple example, we'll just focus on this one only. We don't have 1 plus 1 and 1 plus 3 and all of that. We just for simplification, we only have this now. Okay, 2 plus 2 equals 4. Now the domains will be the digits 0 to 9. Okay, so every value here, every letter here will have a value from the domain, because it will be, eventually it will be a digit. Now, what are the constraints? The constraints will be the conditions here, the equations. So first, we have a constraint here that says that every letter here, every different letter will have different value. Okay, so that's a constraint or a condition inherent in the problem itself, is to assign a value to every letter that is different from the other letters. This is what we mean by all diff here. Of course, this is an implicit constraint. Another constraint that's also implicit is the equation for the first operation here. O plus O equals R plus 10 times x1. Okay, and we can say also W, of course, x1 plus W equals U plus 10 x2, and so on. So we can write all the mathematical equations here that will make this possible. Now, the constraint graph, you see that some constraints don't relate only to variables. So for example, this constraint relates O with R with x1. So how can we represent that in a constraint graph? Let's see. O, R, and x1 are related by that constraint. So if the constraint is relating more than two variables, we draw it as a square, and out of that square there is a line or edge to every variable. Okay, so this is now n-way constraint that relates O with R with x1, which is actually this equation. For another example is that constraint or diff, which relates all of these variables together, and this is the one. Okay, there is a square here, and then there is an edge to every variable in that constraint, and so on. So this is now a constraint graph. That's no longer a binary constraint graph, because there are some constraints that relate more than two variables. But still, this is a constraint graph for this problem. Okay, any question about this? So that's another example of a constraint graph. Hamza? Yes, of course. This is an example of the problem that has nothing to do with map coloring. Yeah. Okay. Any other questions? But here, this is just an example of a constraint graph that is not binary. That's a clear example of a non-binary constraint graph. Okay, let's move on and let's think about varieties of CSPs and constraints. So in terms of variables, we can have, generally in any CSP, we can have discrete variables that have finite domains or infinite domains. In case of finite domains, the domain D, the domain will be of size D, which means that every variable can have a value of D possible values. So D times D times D, that will be order of D to the power n assignments, or possible assignments to the variables. In case of infinite domains, we can have a domain like integers or strings. For example, variables are taking fixed start and end times for each job. I'm scheduling jobs, and I can start only at specific times, hours, for example, but in a very long time. Okay, so it's kind of infinite domains, but still discrete. I can also have continuous variables where, for example, here the variables can be the start and end times that are not fixed. It can start at any time, it can end at any time. So that's an example of continuous variables. In terms of constraints, we saw that some constraints are unary, which means that they relate only one variable, like saying SA is not equal to green, or binary when we relate two variables, SA is not equal to WA, or higher order constraints as we saw in the cryptarithmetic problem. We can also have what we call soft constraints. So for example, I can say for map coloring problem, it's better to have red for Tasmania than green. So that's a preference. We call it soft constraint. It's not a must to have red, but it's better. And usually we represent that by a cost, given a cost for every variable, and the cost will be less if we maintain the preference. Okay, it's like priorities, but still they are not hard constraints, so we can violate them, but we will be rewarded if we don't violate them. We will ignore these kind of constraints until we inshallah reach Bayesian networks, inshallah, later in the course. CSPs solve so many real problems. Many of them are scheduling problems, like when can we all meet, which class is offered when and where, who teaches what class. Okay, if you think about these scheduling problems, for example, the scheduling of teachers, we can have constraints like this teacher can teach only within these times, or this teacher can teach only these classes, or this teacher can teach only these ages, and how you can schedule all the possible classes with all the possible teachers. That's an example, that's a classical example of a kind of problems that are CSP problems, or real-world CSP problems. And many of them, by the way, involve real valued variables, not just discrete. Now let's start to think about how we can solve CSP problems, or constraint satisfaction problems. We will start by a naive search approach. But let's first think again about CSPs in terms of the search formulation that we had before in the course. Okay, the initial state is the empty assignment, and the successor function will assign a value to an unassigned variable, so one value at a time. Okay, so again, what we are doing here, what we are trying to do here, is to formulate the CSP problem as a search problem, as a general search problem. In the search problem, we define what is the start state, what is the successor function, what are the states, what are the start state, what is the goal test, and what is the successor function. So we can say that the initial state is the empty assignment. Nothing is assigned so far to any variable. The successor function will assign a value to one variable that was unassigned before, and the goal test is to is the test whether the assignments, the current assignment, is complete, which means that every variable is assigned a value, and satisfying all constraints. Okay, so we can think of it that way, and let's see how the naive search strategies, naive in terms of knowing the nature of the problem that we discussed earlier, like BFS and DFS, will do when we try to solve a CSP. So we'll start with BFS. So let's say that we will have this this constraint graph, this problem. Again, this is map coloring, and we want to solve this problem with okay, so let me change this. So we'll try to solve this problem with a with BFS. Okay, so with BFS, let's think together. We will start with the empty state, where we don't have any assignment to the variables. So here, let's say that the first one will be WA is red. Okay, we remember in what we said that in every state, in the next state, we will assign a value to an unassigned variable. So one state here will be WA equals red, and we didn't assign the rest yet. Okay, here we can say, for example, SA equal green, and so on. So we can have all the possible states in that tier, the first tier. Okay, now let's say that we are expanding with BFS, and we are expanding the second tier now. Okay, so we'll expand this node to the next states. So the next state from this will be WA equal R and SA equal R also. It can happen, right? It can happen. And here we will have SA equal green and something else. So SA equal green and V equal red. And all possible pairs of assignments will be at the second level. Okay, and again, also this one will have its own second level, and so on. We will continue building the search tree, okay, until, okay, so we'll continue the third tier here, the fourth tier here, okay, and so on, but we will not find the solution until we reach some specific point. Where do you think we will have a possible solution if we do a BFS? Yes, Ghanem? At the end of the tree, which is at the bottom of the tree here. Okay, so at the last tier, so if we do all of these tiers, okay, we are sure that we don't reach a solution, and the solution will always be somewhere here. So that's the first point, that BFS will not be efficient in this case, because BFS will expand the whole tree, tier by tier, until it reaches the last tier. And of course, not knowing anything about the nature of the problem, which is CSP, it doesn't know that, so it will have to explore the entire search tree until we reach the bottom. That's not the only problem with BFS. There is another problem, which is here, for example. If you look at this, will we ever find the solution in the subtree of that node? Of course not, because we know that from that moment, we are violating a constraint. But BFS doesn't know that. BFS just knows whether this is a goal state or not. If it's not a goal state, it will keep assigning a value to an assigned variable. Okay, so BFS will not work here. Maybe DFS, will not find a good solution here quickly. So it's not efficient. So knowing that the solution is at the bottom of the tree, maybe DFS, which will go deep very early, might be more efficient. So let's see what would DFS do in this case. So in DFS, we'll move deep into the search tree, trying to find the solution, and then we will go up and so on. So let's see what DFS will do here. We'll have a demo. In this demo, this is again a constraint graph. It's again like map coloring, but it's a bit larger than the map coloring problem that we had in the previous slide. Still, the constraints are, the variables are the states, and the constraints here indicate that these two states should not have the same value. So we will start DFS by assigning a value to the first variable, which is blue here. So we'll start from this state, and we assign blue. Now DFS doesn't assign, will keep assign. If you remember DFS exploring the search tree, it will go deep. Okay, going deep means that I will not explore tier by tier, but I will keep adding values to the variables until I reach a solution. If not, then I will go back one tier and then try another value. So what will happen here? The next variable is this one. Now guess what value will be assigned to that variable? Not knowing anything about the constraints, DFS will assign a blue value to it. If you look at that, it will be assigned blue here again. It doesn't know that that violates a condition. It will only know that there is a problem only when it has a complete solution. Okay, and doesn't have any more values to assign or variables to assign. So it will keep adding, and if you can run that of course at your own, but if you keep running it, it will assign blue values to the variables. Okay, although from the beginning here we know that there is a violation of the constraint and we should backtrack from here and assign another value to that variable, but it will keep assigning blues until the end. Now, since there is no more unassigned variables, it will backtrack. It will try another value for this variable. So it will try red now. Still, that's not a solution, so it will try to go one step earlier and try to find values for these two variables, and so on until it reaches back up to the first and second tier. Again, this is not efficient. Not knowing about which constraint are violated is a big problem. So we need these two examples of trying BFS and DFS shows us that we need a solution that is aware of the nature of CSP, that is aware of the constraints, and will be very specific to make sure that some of the constraints should be checked at earlier times so that we can avoid wasting a lot of time in solutions that are doomed, solutions that are known very early or can be easily known very early that they are not actually solutions. Abdurrahman. Yes, exactly. Yes, exactly. I didn't want to say that. Okay, by solving problems, the book has problems. You have now the homework, and also the project will be inshallah released probably tonight or maximum tomorrow. You will practice a lot. Don't worry. Okay, you're welcome. Any questions about the lecture now? Okay, so with that, inshallah, starting next lecture, we will see specific solutions that are aware of CSPs, that are much more efficient than BFS and DFS in solving CSP problems. Talk to you, inshallah, on Tuesday. Assalamu alaikum wa rahmatullahi wa barakatuh.